So Assalamualaikum student, we are in the last chapter of CHE245, Fundamentals of Thermal Radiation. So it took me, this topic is actually quite long, so I need to find a simpler way to explain the fundamental concept of radiation in a simpler way to you. So these are all the objectives for this chapter. Okay. Actually for chapter 6, we've divided it to two parts. So this one is for black body concept and the other one is for view factor. So unlike conduction and convection, radiation does not require the presence of a material medium. So it's actually the radiation is magnetic waves or electromagnetic radiation. It present the energy, energy emitted by a matter as a result of the changes in electronic configuration of the atoms or molecule. So your waves, lambda is equal to c speed of propagation of a wave in that medium divided by frequency v. But normally the question will straight away give you the lambda. So we have learned the term black body back in chapter 1, where black body is a perfect radiation absorber and emitter. It is actually the maximum amount of radiation that can be emitted by a surface at a given temperature. So back in chapter 1, we say for black body E, small e is equal to 1, emissivity E, is equal to 1. And it can, emits energy uniformly at all directions per unit area normal to the direction of the emission. So your energy is uniform, unlike for a real body where the energy is non-uniform. The amount of energy emitted from a surface is actually depends on the material of the body, and the condition of its surface. Condition here is refer to the roughness of the surface and also the surface temperature. So the radiation energy emitted by a black body per unit time and per unit surface area introduced by Stephen Boltzmann law, the energy, radiation energy, or we also call it as radiation power, total radiation power, EB, capital E is equal to theta times T power of 4 in watt per meter square. So your theta is 5.6 times 10 power of 8, and you have to make sure you convert your temperature in Kelvin before you start your calculation, because this formula is only valid for Kelvin. And don't get confused with the capital E and the small e. Small e is emissivity, where it is unitless. The small e emissivity does not have a units, while for the radiation energy or radiation power, the units is watt per meter square. One thing, example of approximate black body. The black body, black here does not refer to color. So black body does not necessary to be black in color. So other example include snow, white paint, and also large cavity with a small opening. So here you have they give you the image of large cavity with a small opening of area A. So this one is also one example of approximate black body. And sometimes we are also interested to know the radiation energy at specific wavelength, lambda, at specific lambda. So for here, equation 12.4, this one is valid for gas and vacuum. But for other mediums, you need to modify this equation by dividing the constant C1 divided by n to the power of 2, where n is your refractive index. And okay, that is only applicable for other medium except besides the gas and vacuum. For gas and vacuum, you can just straight away use this constant C1 and C2 and replace lambda and T at your interested wavelength and temperature. Okay, the figure here shows the variation of thermal blackbody emissive power with respect to wavelength. It's EB lambda versus wavelength. So here you can see that the peak here is log maximum. This is the relationship. It's actually depending on the temperature. So as your temperature go lower, okay, so as your wavelength become higher, your temperature actually go lower, your peak temperature. Okay, so let's look at this example 12.1. So consider you have a 20 cm diameter spherical ball at 800 K suspended in air as shown in figure 12.12. Assuming the ball closely approximates as a black body, determine A, total black body emissive power, B, total amount of radiation emitted by the ball in 5 minutes, and C, spectral black body emissive power at wavelength 3 micrometer. So EB, for the first part A, we just straight away use that equation. EB equals to theta times T power 4. Okay, so this is a constant, theta is constant, and your temperature is already in Kelvin, so just plug in that number and make sure it's power 4. So you get 23.2 kilowatt per meter squared. So in part B, the question specifically asks you the amount of radiation emitted by the ball in 5 minutes. So you need to use the answer from part A and multiply it with surface area and time. Okay. So surface area of a spherical is equal to pi d squared. Okay, and you need to convert your time in second because in this equation you have watt. Okay, watt is joule per second, so you need to to cancel that out. You need to make sure your time is also in second. So just for the total amount of radiation, you need to is equal to total radiation energy multiplied by surface area multiplied by delta T time. Okay, and you will get 875 kilojoule. So for part C, the question said the spec is interested to find you need to find the spectral blackbody emissive power at specific wavelength. Okay, they give you wavelength of 3 micrometer. And this one, the medium is air, so you can straight away use equation 12.4. So just substitute the value of C1 and C2 at the given lambda and T temperature. So at the end you will get 3846 watt per meter square micrometer. Okay, so this is quite straightforward. You just have to plug in in the equation that we have learned in previous slides. Okay, so let's proceed. We often interested in the amount of radiation emitted over some wavelength band. Okay, the range of the for some wavelength range. So the equation is given by this. Okay, where it needs to do some integration. But this integration does not have a simple closed form solution. So we introduce a dimensionless quantity f lambda, okay, called the blackbody radiation function, where actually represented by the area under the curve divided by theta lambda, theta t power of 4. Okay, where n is equal to 1 or 2. N is the lambda. Okay, the values of f. So someone has do the correlation and determine the area under the curve at specific lambda and t temperature. So okay, so for the first part, 12.4 is at lambda 1, lambda 1 to lambda 0. So you can use this form, or if the question asks you for from lambda 2 to lambda 1, you need to you cannot take lambda 2 only, because for lambda 2 is cover the whole area from 0 to lambda 2. So you need to subtract with f lambda 1. So the table here they give you is actually in 2 columns. The list is continue here, 6,000, 6,200. This one is not just in temperature, but is lambda times T times temperature in Kelvin. And if you know your lambda and temperature, you can just use the table to know what is your f lambda. So like for this example, this graph 12.9, so if you're interested to know the area under the curve for lambda 2, in between lambda 1 and lambda 2, so first you need to get your values for f lambda 2, then minus by f lambda 1. So let's look at example. Okay, charge coupled device CCD image sensor that are common in modern digital cameras respond differently to light sources with a different spectral distribution. Daylight and incandescent light may be approximated as black body at the effective surface temperature of 5,800 Kelvin and 2,800 Kelvin respectively. Determine the fraction of radiation emitted within the visible spectrum wavelength from 0.4 micrometer to 0.76 micrometer for each lighting sources. So your range is between 0.4 micrometer to 0.76 micrometer, and you need to find the fraction for both daylight and incandescent light. So let's start with the daylight. So you know your lambda 1 and lambda 2, and multiply it with temperature. Okay, and you need to go to table 12.25, 12.2 to find the corresponding f lambda at each wavelength. So these are the values. Okay, if you need to do interpolation, please do so. Okay, because here the gap is 200 lambda t. So but the values here in like 4408, so you need to do interpolation to get the corresponding f lambda 2. So for first part, for daylight, f lambda 2 minus f lambda 1, it is 0.426. Okay, the next one is for incandescent light bulb. Okay, so take note, there is a typo. It should be 0.76 multiplied by 2800. Okay, if you plug in your calculator, you still get 2128. So this is just a typo. So repeat the same method. Okay, f lambda 2 minus f lambda 1. So for incandescent light, you will get 0.087. So since the question only asks for the fraction, so this the final answer for each type of lighting sources. But if the question asks you for the total energy, you need to multiply, okay? Because here, if you are interested to the whole energy, from these two wavelength. So you need to multiply